Have you ever pondered what would happen if you could travel close to the speed of light? Welcome to the fascinating realm of relativity, a theory that changed our perception of space and time. This groundbreaking theory was proposed by Albert Einstein in the year 1905. Einstein's special theory of relativity is underpinned by two fundamental postulates. The first one suggests that the laws of physics are the same in all inertial frames. In simpler terms, whether you're standing still or moving at a constant speed, the physical laws remain the same. The second postulate asserts that the speed of light in a vacuum is constant, no matter how fast you're moving. It's always approximately 300,000 kilometers per second. These theories, as simple as they may seem, led to profound implications that shook the very foundation of our understanding of the universe. So, how does this theory change our perception of the world? Hold that thought. Scene script: imagine you are on a spaceship traveling near the speed of light. How would time behave? In the world of relativity, time is a peculiar fellow. It doesn't always tick-tock in the way you'd expect. This brings us to a fascinating concept known as time dilation. Picture yourself on a train, watching a bouncing ball. To you, the ball bounces up and down in a straight line. But to someone standing outside, the ball traces a diagonal path as the train moves forward. Now replace the bouncing ball with a light beam and the train with a spaceship. The light beam is bouncing between two mirrors, forming a light clock. To you, inside the spaceship, the light beam seems to move straight up and down. But for an observer outside, the light beam follows a longer diagonal path. Here's the kicker: the speed of light is always constant. It doesn't matter if you're standing still in a moving train or a spaceship hurtling near the speed of light. This means that the light in our spaceship clock, which has to travel a longer diagonal path, takes more time to complete a tick-tock cycle from the perspective of an outside observer. But from your perspective, inside the spaceship, time appears to be running normally. This is time dilation. Moving clocks run slower compared to stationary ones. But remember, it's all about perspective. If you're the one in the spaceship, you wouldn't notice anything amiss. Your wristwatch isn't going to suddenly start dragging at second hand. It's only when comparing your clock to those left behind on Earth that the difference becomes apparent. So, if you embarked on a cosmic joyride at near light speeds, you might return to find Earth has aged more than you. Time for you would have dilated, stretched out like a piece of cosmic taffy. That's the crux of time dilation, a theory that sounds like it's straight out of a science fiction novel, but is very much a part of our reality. It's a direct result of the constant speed of light, a postulate of Einstein's special theory of relativity. In other words, time flies when you're fast, but what about space? Now consider this. What would happen to space if you're traveling at nearly the speed of light? This question brings us to the fascinating concept of length contraction, a brain-bending phenomenon predicted by Einstein's theory of special relativity. Length contraction suggests that the length of an object in motion as observed from a stationary frame of reference will appear shorter than its actual length in the direction of motion. Let's say we have a spaceship zooming through the cosmos at a speed approaching the speed of light. Now, if you're an observer stationed on a distant planet, watching this spaceship fly by, you'd notice something peculiar. The spaceship would appear shorter to you than its actual length. It's as if someone has squished it in the direction of its travel. This might sound like a trick of the light or an optical illusion, but it's not. It's a genuine physical phenomenon. The spaceship is genuinely shorter in your frame of reference. This is not about the way the light from the spaceship reaches your eyes. Instead, it's about the very nature of space and time themselves. Remember, this isn't a result of the object physically changing shape or size. The spaceship hasn't shrunk or been squashed. If you were aboard the spaceship, it would look perfectly normal to you. This effect is entirely relative to the observer's perspective. This might be a tricky concept to wrap our heads around as it defies our everyday experience. We're used to thinking of lengths as fixed, absolute quantities. But in the realm of high speeds and relativity, the ordinary rules of geometry don't apply. What we perceive as the length of an object can change depending on our relative motion. This is one of the many mind-bending predictions of Einstein's theory of relativity. It tells us that the universe is much stranger and more flexible than we might have thought. It's a vivid demonstration of how our common-sense notions about space and time can be turned on their head when we venture into the realm of the extremely fast. So, Einstein's relativity shows us that space and time are not as constant as we once thought. Why should we care about the special theory of relativity? Is it just a concept for physicists and science nerds? Well, not quite. Let's delve into why it matters in our everyday lives. Albert Einstein's theory of relativity isn't just an intellectual exercise, it plays a vital role in technologies we rely on every day. Take GPS technology, for instance. The global positioning system, the little magic that helps us navigate through cities or across continents, needs to factor in relativity to function accurately. Satellites are moving rapidly compared to observers on Earth, and according to relativity, time ticks slower for them. This difference, although minuscule, matters. Without correcting for this time dilation effect, your GPS coordinates could be off by several kilometers. Let's shift gears to the world of particle accelerators, the colossal machines probing the frontiers of physics. Here, particles are accelerated to speeds close to that of light, and the effects of relativity become prominent. Without understanding relativity, we wouldn't be able to predict their behavior accurately, and our pursuit of the fundamental constituents of the universe would hit a roadblock. Moreover, the theory of relativity has reshaped our understanding of the universe itself. It's provided us with a framework to understand the cosmos on the grandest scales, from the dance of galaxies to the expansion of the universe. It's even given us insights into the nature of black holes, those mysterious cosmic objects where space and time warp to extremes. But perhaps the most profound impact of relativity is on our conception of reality. It's taught us that space and time are intertwined in a four-dimensional fabric called space-time, and that the universe is not as straightforward as it seems. It's shown us that time is not absolute but relative and can slow down or speed up depending on how fast you're moving or how strong is the gravity you're experiencing. In a nutshell, Einstein's special theory of relativity has given us a new perspective on the universe, where space and time intermingle and nothing is as it seems. It's a testament to the power of human curiosity and the quest for understanding. Who knew that traveling close to the speed of light could be so enlightening?